So at this time, I would like to welcome to the stage Radia Perlman. She is going to be delivering our keynote, Do the Wrong Thing. Welcome, Radia. As she walks up. So as Radia joins me, Radia Perlman is a fellow at Dell EMC. She is known for inventing fundamental technology enabling robust, largely self-managing and scalable link state routing used in the specific protocol she designed, ISIS, and similar protocols, OSPF. She also invented the spanning tree algorithm, which transformed Ethernet from a technology that supported a few hundred nodes within a single building to something that could support large networks. Radia has made contributions in network security, including scalable data expiration, distributed algorithms despite malicious participants, and DDoS prevention techniques. She is the author of the textbook Interconnections about network layers 2 and 3, and co-author of Network Security. Radia has been recognized with many industry honors, including induction into the National Academy of Engineering, the Inventor Hall of Fame, the Internet Hall of Fame, Washington State Academy of Science, and Lifetime Achievement Awards from Usenix and SIGCOM. She has a PhD in computer science from MIT. Welcome, Radia. We are very excited to have you speaking with us today.
So, as it turns out, I thought that I would have less time than I do. So I have an extra slide with a whole bunch of random things I could rant about it, if there will be time, and there probably will be. And it's great to hang out with you guys because I'm not hands-on. So I actually learn a lot from, it's good to share ideas. Anyway. So I'm going to be talking a lot about history in order to sort of frame things in a different way than you may have been thinking about. I'll talk about two decisions that I thought were disastrously bad. One was assuming that Ethernet was a network instead of a link in a network, and not adopting CLNP, whatever that is, I'll tell you, in 1992. And then surprisingly good things that I believe would not have been invented had we not made the wrong decisions back then. So understanding network protocols. I just can't imagine what it's like to jump right in and like some of these courses about things, it's like, well, this is how you configure this obscure thing. Nobody would have designed what we have today. So if you actually believe that it makes sense, you'll just sort of drive yourself crazy. So you have to kind of understand the history in order to understand how we got there. So how networking tends to be taught is as if TCP/IP arrived on tablets from the sky in its awesome perfection. You know, there's nothing else could have existed. You know, there was no way to have made it better. And the way you teach it is you have your students memorize the details of the current standards so that they can graduate and immediately be able to manage, you know, Cisco routers or whatever. And if you ever talk about any alternative technology, it's always to just sneer at it about what idiots those people were. So things are always so confusing to me. And whenever there's two similar things like Ethernet and InfiniBand, I get very curious. It's like, what are the intrinsic differences between these things? And nobody does that. So you either have experts in A or experts in B. And so people hand me the two specs, and they're two huge specs with their own jargon for no good reason. And if I'm sort of having a headache reading these specs and I ask an expert in A, how does it compare with B? They'll say, oh, A is awesome and B sucks. And you ask a B person, you get the opposite answer. But then if it turns out that as the industry is sort of debating these things, that B has some features that A doesn't have, no problem. The A people steal the ideas and put it into their spec. And it turns out nobody really cares about the details of their spec. They just want credit for it. So they're willing to take the other technology completely as long as it's claimed to be their thing. Standards bodies, it's sort of natural to think of them as sort of well-educated technologists that are carefully weighing engineering trade-offs. But a much more accurate way to think of them is as drunken sports fans, you know. I'm getting a feel for the audience here of what I can get away with. Apparently, I can get away with a lot. So in order for me to sort of explain this stuff, we have to review network layers. So ISO happens to be a different sports team, was credited with naming the layers. And it's just a way of thinking about layers. It's not like, you know, you don't have to take it seriously in any sense. So this is kind of the way that I mean, I call it Perlman's layers, and you'll understand in a minute. So the bottom layer is the physical layer. It's how I signal a bit from me to somebody else who's on the same wire. You know, what does the cable look like and so forth. Layer 2 is how do you talk to somebody who's on the same wire as you are, given that layer 1 lets you signal bits. So it's like in the stream of bits, how do I signal this is the beginning of a packet, this is the end of a packet, this is a checksum. Layer 3 is the thing that forwards from link to link to link. And because of that, things can get out of order and so forth, or lost. So layer 4 is the thing that the source and destination number the things and put them back in order, ask for acknowledgements and so forth. And layers 5 and above are boring. So Ethernet and IP. So Ethernet's layer 2, right? And IP is layer 3. Well, if Ethernet is layer 2, why are we forwarding Ethernet packets? Well, oh, but it's a switch that's forwarding it. So that's different somehow. So it's not really forwarding. Well, as it turns out, a switch, a bridge, a router, whatever you want to call this box, receives a packet, looks at the header, sees what the destination is, has somehow acquired a forwarding table that says for each destination which port to send it out. So there's no difference there. So how did we get to be forwarding Ethernet packets? So the original Ethernet was a way for, oh, everyone knows that Ethernet is wildly successful. And no, it's not. It died many, many years ago. What Ethernet is or the original invention was a way for a few hundred nodes to share the same wire. And if two of them talk at the same time, they'll interfere with each other. So it's how do you manage without one main guy that calls on everybody else and gives them permission to talk? How do you manage to do it? And the protocol was called CSMA-CD. CS is carrier sense, means be polite and listen, and if someone else is talking, don't talk. Multiple access just means there's lots of nodes. And collision detect means even while you're talking, you listen to see if somebody else might talk at the same time, in which case you both stop and you start again a random time later. And there were zillions of papers about minor modifications to this, but basically, you know, if you try to load it with too much traffic, there'll be so much collisions that you'll get less and less useful traffic through. So I was, at that point, innocently doing layer 3. At Digital. And my routing protocol, unfortunately, got named ISIS. So a few years ago, apparently Trump said that Hillary and Obama invented ISIS, and a bunch of my friends noticed this and forwarded it to me and said, shouldn't you get some credit? But at any rate, so the kind of protocol I was doing, I call it a link state protocol. Here's a picture of a network. There's like 7 nodes. A line between A and B means they're neighbors, and the cost of the link is 6. Each one of the nodes creates what I call a link state packet, which talks about the state of your links. So in this case, that link state packet says, I am C. I have a neighbor B at a cost of 2, F at a cost of 2, and G at a cost of 5. And if you look at C there, you'll see it has 3 neighbors. And that link state packet gets distributed to all the other nodes. And so everyone has the same database, which is the most recently generated link state packet from everybody else. This gives you all the information you need to draw a picture of the network or calculate paths. So then, with great fanfare, Ethernet arrived. And so everybody was so excited. This is the new way of doing networking. And I looked at it and I said, whoops, this link has different properties than I was expecting. So I modified ISIS a little bit to accommodate this type of link. And in particular, the database associated with the link state protocol is proportional to the number of links in the network. So if you had an Ethernet with 500 nodes and everyone reported 499 neighbors, that would be a lot of, the database would be big. So I just did a little thing, like I said, oh, instead of considering an Ethernet as n squared links, instead create a fictitious link, which is the Ethernet itself. Everyone just reports that they're connected to that. So you'll have n plus 1 nodes and n links rather than n squared links. But, you know, I didn't think that was a big deal. But unfortunately, the world, you know, because they didn't call it Etherlink, they called it Ethernet, people were building applications that worked directly on Ethernet. So in their network stack, they didn't have layer 3. So I tried to argue with them. And I said, no, you still need layer 3. And they said, oh, Radia, you're just upset because no one needs your stuff anymore. And I said, oh, but you may want to talk from one Ethernet to another. And they said, our customers would never want to do that. So, a router can't forward unless the end nodes cooperate and put the right envelope on their packets. So, at any rate, the people who were doing this made lots of money for the company because their applications were good. They would have made just as much money and their applications would have been just as good, better even, had they done it correctly, which was on top of layer 3. But it's hard to explain that to management. So I was, kind of in a bad mood about the whole thing when my manager came to me one day and said, Radia, we need to design a magic box that will sit between 2 Ethernets and let somebody on one talk to somebody on the other, which is what my entire career had been about. But the constraint was without modifying the end nodes. So we've deployed all these end nodes that just think they're speaking on a single CSMA-CD link. And there was no spare fields in the Ethernet header, and there was a hard size limit. So basically, they had the basic idea at that point, which was just to build this box that listens promiscuously, meaning listens to every single packet, stores it up, and when the ether is free on some other port, or it gets the token if it were a token ring, it forwards the packet. And, an extra optimization is learning based on the source address. So in this case, the box has learned because A has transmitted a packet. So it looks at the source address in the port and it says, A is on that port. And so then if J were to transmit a packet for A, it would say, A has already gotten it. I don't need to forward it. Whereas if A were to transmit a packet for J, then it has no idea where J is, so it forwards it on both ports. So this is all fine, except for if there's loops, because the Ethernet header doesn't have any hop count. So things will just go round and around. And how can you learn the source address if it might come from multiple directions? So what do you do about loops? Well, one possibility is you just tell the customers, well, be careful when you plug it together not to put in loops. But loops are not bad things. It just means that there's an alternate path in case something dies. So this was what my manager asked me late on a Friday before he was going away for a week. And this was before people read email or had cell phones or anything. So he was going to be absolutely gone. And he thought, so he said, oh, radio, you do this distributed algorithm stuff. Come up with something that with zero configuration, you can plug together any topology, and these things will figure out a loop-free subset for actually forwarding data. And then he thought it was going to be really hard, because zero configuration, break all the symmetries. And so just as he thought he was being witty, he said, oh, and furthermore, make it scale as a constant. So the amount of memory necessary to run this thing should be a constant no matter how many bridges and links there are in the world, which is crazy. Nothing's a constant, maybe linear if you're really lucky, probably n squared. So he went away, and that night I realized, oh my goodness, it's trivial. And I could prove that it worked. I knew just how to do it. And it was so trivial, I wrote the spec on Monday and Tuesday, and it was complete enough that the implementers got it working in just, a few weeks without asking me a single question. So, but that was Tuesday, and I couldn't concentrate on anything else until I could show up to my manager, who was not around. But at any rate, what does the spanning tree do? The circles are bridges, the green lines are Ethernets, and the black lines are ports from the bridge to the Ethernet. So you plug it together any which way, spanning tree algorithm runs, and so the bridges decide certain ports are redundant, and they will not forward packets to or from those ports, but they'll still running the spanning tree algorithm just in case the topology changes. So the path from A to X, if A transmits a packet, it'll go all that way to get to X. And you might think, well, that's pretty silly. If it were a smarter spanning tree algorithm, you would have gotten better paths. But no, if you have a single shared loop-free topology, you're not going to get optimal paths all the time. Because if you imagine the topology being a big circle, then the spanning tree has to break it someplace, and people on either side of the break have to go around the long way. So shortly after that, like a year or two after that, CSMA-CD kind of died out. Nobody does that anymore. There's, variants of it on wireless links, but on wired links, it's all point-to-point links with switches. So Ethernet today has nothing to do with the original CSMA-CD invention. So as I said, I couldn't concentrate on anything else. And so the remainder of the week, I spent working on the poem that was the abstract of the paper in which I published this thing. So I officially spent more time on the poem than I did on inventing the algorithm and writing the spec. So the poem, and apologies if you've heard the poem already, but when I mentioned I was doing this, they said, oh, make sure to do the poem. So, okay. Algorhyme, because every algorithm should have an algorhyme. I think that I shall never see a graph more lovely than a tree whose crucial property is loop-free connectivity, a tree which must be sure to span so packets can reach every LAN. First, the route must be selected. By ID, it is elected. Least cost paths from route are traced. In the tree, these paths are placed. A mesh is made by folks like me. Then bridges find a spanning tree. So why was bridging so popular? I mean, it was really sort of a kludge just until people fixed the end nodes to put layer 3 back, or at least that's what I believed. At the time, there were lots of layer 3 protocols, IP, IPX, DECnet, AppleTalk, and a bridge just worked. There were multi-protocol routers, but they were slow and expensive, whereas, and horrible to configure. And bridges, you just plug them in and they work. And somebody once told me, hey, you know, some of our customers are complaining that bridges are the most boring thing that digital ever did. You just plug them in and you can't do anything with it. And I said, fine, if they want knobs, I'll put in knobs, but they don't have to touch the knobs. And if they do touch the knobs, any configuration will still work. So that's sort of my philosophy of things, that things should just work, but for people who like to play with it and maybe tune it a little bit, let them play, but don't let them hurt themselves. So spanning tree Ethernet is a kludge. You don't get optimal paths. Unused links don't get used, you know, things that are not in the spanning tree, and the other links have more traffic than they would have otherwise. Temporary loops are incredibly dangerous because the header has no hop count. Now, why isn't there a hop count in the Ethernet header? It wasn't like the inventors didn't know about hop counts. It never occurred to them that anyone would be foolish enough to be forwarding these things. So yeah, it's just incredibly scary because you can't make everybody's forwarding tables immediately switch to a new topology. If things change, then there'll be a time when they'll be sort of out of sync and packets may loop around. And worse than that, with Ethernet, if you have a bridge with 7 ports, when it receives one packet, it will make 6 more packets. So you not only have a single packet sort of wandering around, but you multiply the numbers of them, which can starve out any attempt by the routing algorithm to redo the forwarding tables for the new topology. So why not get rid of Ethernet these days and use just IP, given that everything is just point-to-point links? The world has converged to IP as the layer 3 protocol, and all of the end nodes have IP in the stack. So all the original reasons for needing bridges go away. So why hasn't it gone away? On a link with 2 nodes, a point-to-point link, why do you need a 6-byte addresses to say who you are and who you're sending it to? It's like, if you're hearing this, it's for you. And you know, if you're hearing it, it's from me. Why can't you just forward things with layer 3? So if IP were designed differently, we wouldn't need the Ethernet header anymore. So today there's 2 headers, the layer 3 header and the layer 2 header. So when S talks to D, the layer 3 header will say the source is S and the destination is D, and that will never change. But the layer 2 header gets replaced at each hop, unless you have a point-to-point link, and then you don't need the header. If you have everything having point-to-point links, you really don't need those addresses anymore. You could just forward it with layer 3. So what's wrong with IP? IP is configuration intensive. You can't have like a data center with a flat address space where you can move VMs around without changing their address. You wouldn't be able to do that if everything were connected with IP. Because every link in IP, where a link is defined as a different port on a router, has to have its own block of addresses. And the routers have to be configured with which block is on each port. And if something moves from one side of a router to another, it has to change its layer 3 address. So people would like to have a cloud with a flat address that within there you can move around freely. Now, layer 3 doesn't have to work that way. That's how IP works, but there are other layer 3, or there were other layer 3 protocols that acted differently. In particular, there was one done by ISO, I guess, a different sports team, called CLNP, which stands for Connectionless Network Protocol. And at Digital, when I took over layer 3, we had 2-byte addresses, and I said, we need bigger addresses. And I didn't say, wow, if I design my own header, my own packet format, maybe I'll win a Nobel Prize. You know, it's like, fine, this ISO thing looks fine. It has 20-byte addresses. Let's just use that. So DECnet also adopted that. So it was a 20-byte address where the top 14 bytes were a prefix just like IP that gets you to a cloud. But once you get to the cloud, all the nodes there share the same prefix, but the cloud routes to the individual end node within the cloud. And so the end node has to cooperate a little bit by telling the routers where it is. And then you can have optimal paths inside of there and so forth. So CLNP has this 14-byte prefix that has as many levels of hierarchy as you want, but it terminates at the 14-byte prefix, and then inside is a cloud with a flat address space where you can move around. CLNP also had other features. It had auto configuration, and the way that it did that, it said stick your Ethernet address, your MAC address, into the bottom 6 bytes. It also had plenty of addresses. So it had 20 bytes versus IPv6 only has 16 bytes. And the high order part in CLNP was 14 bytes rather than in IPv6 where it's only 8 bytes. And the bigger the prefix, the easier it is to kind of hand out addresses. And it was widely deployed. It supported large customer networks. IP depends on something else creating a cloud with a flat address space. So there's ARP called neighbor discovery and IPv6, sort of the same thing. Once IP gets to what it thinks is a link, it then has to do ARP to say, hey, who has this IP address? And someone says, I do, and this is my layer 2 address. And then the router can forward it. So if you have IP plus Ethernet, IP gets you to what IP thinks of as a link, and then you have to do ARP to get your address within that link, and then some other magic technology, whether it's CSMA-CD or spanning tree or Trill or VXLAN, makes a bunch of links look to IP like a single link. Whereas with CLNP, the top 14 bytes get you to the cloud, and then you don't need to do ARP. The rest of the address is right there in the layer 3 address, and you have true layer 3 routing inside with a hop count and civilized protocols and stuff. So with hierarchy, if you have one prefix per link, you have to carve up the address space and do a lot of configuration. With CLNP, inside one of these clouds, 0 configuration. You just plug together the routers and the end nodes. Nobody has to know anything except one guy has to be told what the 14-byte prefix for the cloud is, and it lets everybody else know. But other than that, you move around, no configuration. So what I used to say was the single worst decision in the history of mankind until, we've made worse ones since, I suppose. Maybe not this industry, but at any rate. So in 1992, people said, IP addresses are too small, 4 bytes. How about if we adopt this CLNP thing? And so the routing vendors were behind it because they already had it implemented and stuff. Somebody modified TCP to work on top of CLNP, in which case immediately all the internet applications worked because they worked on top of TCP and they didn't have to change to have bigger addresses underneath it. It was much easier in 1992 to migrate to a new address format because the internet was much smaller. It wasn't so mission critical like it is today. And IP hadn't yet, out of necessity, invented DHCP and NAT, which we'll talk about in a minute. So CLNP gave understandable advantages. So the whole idea of no ARP, no configuration inside the flat address and all that. So the decision was, let's invent something new and let's call it IPv6. So IPv6 is just a 16-byte version of IP with 8 bytes for prefix and 8 bytes for node ID on the last link. 8 bytes on the top is inconveniently small for administering addresses. 8 bytes on the bottom is way too much, especially once DHCP got invented. So it's technically inferior to CLNP because IPv6, just like IPv4, needs to have a different block of addresses on every side of an IP router. And so IPv6 still will depend on some other thing to magically create a cloud with a flat address space. And it's no more compatible with IPv4 than CLNP is. There was all sorts of silly hype, like that it has 2 to the 128 addresses, so you can number every molecule in the universe and things like that. And in general, when you have hierarchy, you waste addresses, but there's only 8 bytes to play with, or that it has security built in versus IPv4. I decided that that's deferred to the last slide if you want to hear me rant about that, where that came from. So is IPv6 just a new version of IPv4? So let's look at what's a version. Well, in the IP header, there's a field called version number. It's a 4-bit field. And for IPv4, you put a 4 there. For IPv6, you put a 6 there. So what exactly is a version number? What's the purpose? Is it decorative, or does it serve some sort of purpose? So there's a philosophical question about what's the difference between a new version of a protocol and a different protocol. And the only thing that makes sense, at least to me, is that you have an envelope, like an IP header or an Ethernet header, that basically says which process should receive the packet. So in Ether, it's called an Ether type. In IP, it's called a protocol type. In TCP and UDP, it's called a port. So if you have, the protocol type says which process to give the packet to. If you have 2 different processes, even if they are implementing the exact same protocol, if they're using different protocol types, then they're different protocols. Whereas if you want to share a protocol type and then differentiate based on the version number, then no matter how different they are, they're different versions of the same protocol. So if you differentiate based on the version number so that you can share the same protocol type, you can't just say, write this value into this field. You have to also say, if you receive a packet, look at the version number, and if it's not something you understand, then throw away the packet. But they didn't say that in IPv4. So they realized that if they share a protocol type and you send an IPv6 packet to an unsuspecting IPv4 node, it will just happily assume that these 4 bytes are the destination address and this is the hop count and things like that. So therefore, IPv6 can't share a protocol type. So, an Ether type. So IPv6 is a new protocol rather than a new version of IP. So what were the reasons not to adopt CLNP at the time? It seemed like the obvious thing that ought to be done. So one was, it would be ripping out the heart of the internet and putting in a foreign thing. Or, we don't like ISO layer 6, which has nothing to do with replacing layer 3 with 20-byte addresses. We're not immediately out of IPv4 addresses, and those other people are total morons, so I'm sure we will come up with something much more brilliant. So, and the unsaid thing was, but it's a different sports team. We don't want to give them the satisfaction of saying anything they did was worthwhile. So now, alternate history. Stuff that never would have been invented without these bad decisions. So if we had treated Ethernet like a link rather than a network, end nodes would have used layer 3 with ISIS to forward between links. The Ethernet header would have died out. Spanning tree Ethernet wouldn't have been invented. I've heard that the spanning tree algorithm is used in other contexts because it's sort of incredibly simple. And the baked-in MAC address is actually useful for lots of things. So even if we didn't have the Ethernet header, the fact that we're manufacturing all of our devices with a baked-in unique 6-byte ID, people find uses for that. Though privacy advocates get upset about a baked-in unique ID. They think, oh, you're trying to track us or something. So, like Intel got completely undeserved bad press for having a processor ID. Even though there's lots of sort of unique IDs. There's the MAC address, for instance. But yeah, so people, there's mixed feelings about having this unique ID built into your machine. So if Ethernet had remained CSMA-CD, I don't see how we could have had fast Ethernet. CSMA-CD requires detecting collisions within the time it takes to transmit a minimum packet. So if the speed is X times faster, the cable length has to be 1X as much, or you have to increase the minimum packet size. So the original 10 megabit Ethernet was about a half a kilometer. So a 10 gig CSMA-CD link would have a maximum length of a half of a meter. So it doesn't matter because we're not using CSMA-CD. So spanning tree Ethernet also allows IPv4 a much longer life. Links in IP would have been limited to a single LAN, hundreds of nodes. And there would have been no ability to have a cloud with a flat address space. And spanning tree Ethernet was widely deployed by 1992. So maybe if it hadn't been, they would have had the good sense to adopt CLNP at the time. So if we had adopted CLNP, what we think of as layer 2 would have just been the level 1 routing in ISIS. The cloud would have been just, the bottom routing based on the bottom 6 bytes of the address with optimal paths and hop counts as opposed to like spanning tree. And the Ethernet header would have been unnecessary, so extra 14 bytes or whatever it is. But here's some good stuff we probably wouldn't have thought of. So DHCP, how do end nodes get their address? Well, CLNP and IPX said take your 6-byte baked-in address and stick it into the layer 3 header. AppleTalk had an incredibly cute hack for doing auto configuration with only 3 bytes, but at any rate. With IPv4, originally you had to do manual configuration, and then they came up with DHCP, Dynamic Host Configuration Protocol. So what happens is that if you plug into what's supposed to look like a single link to IP, you kind of shout and say, hey, I need an IP address that makes sense on this link. And, who's a DHCP server? And the DHCP server has a pool of IP addresses that are for that link. And it will say, oh, this is an IP address you can use that's on this link. So you sort of get a temporary address for where you happen to be plugged in. Now, would DHCP have been invented if we had adopted CLNP? We wouldn't have needed it as much, but CLNP is a wondrous thing. CLNP already had auto configuration, but DHCP is a much better way of doing it because you don't need to have 6 bytes to have your link local address. 3 bytes is enough, 4 bytes is way more than you would ever need. So you could have bigger prefix within whatever the address is, or you can have smaller addresses. Also, this privacy thing, if wherever I were, if somebody knew what the MAC address of my laptop was, and they saw an IP packet going on and they saw that my well, a CLNP, if they saw my MAC address in there, with the Chinese prefix, they could say, aha, Radio's visiting China right now. But with DHCP, you get sort of a temporary thing for where you happen to be. So another cool thing is NATS, Network Address Translation. So there's this box. Your private network has a block of addresses that have no meaning outside of your network, and lots of private networks can have the same block of addresses. And you have this magic box called a NAT, which has a pool of globally reachable addresses. And when somebody outside just cannot actually talk to anybody inside your network unless the thing inside your network talks first. So if G talks to Z, which is some server on the internet, it'll say the source is G, my local address, and the destination is Z. And the NAT box says, oh, okay, I have to give this guy a globally reachable address. And so it makes a mapping saying that the local address G is the global address K, and it rewrites the source address as capital K. And then when Z returns the packet, it'll say, I'm the source Z and the destination is K, and the NAT box will replace that with the local thing. So the properties of NAT are that nodes inside the private network can't be contacted from outside unless the inner guide talks first, which is a wonderful security thing, actually. It lets us live with IPv4, perhaps indefinitely, and a case can be made that IPv6 with its 16-byte address doesn't give you anything you can't get with IPv4 plus NATs. And not only can a case be made for it, but a very eloquent case was made by Jeff Houston in his talk in defense of NATs, which is both the audio and the slides are on the net. But there was this amazing hatred of NATs. Especially by the people that really wanted to see IPv6 deployed. They were seeing NATs were causing IPv6 not to get deployed. So one thing they were saying was, we should not help NATs by documenting how they work. Now, I was helping to sort of design a protocol, IPsec, that needed to work through NATs. And there was no documentation. And furthermore, the NATs worked slightly differently. So to try to design your protocol so that it would work through any of these NATs was painful. Another one was with IPsec, there were two headers for an encrypted data packet, a cryptographically protected data packet. One was AH for authentication header, which was just integrity protection. And ESP was originally just encryption. And so if you wanted to have a packet that was IPsec cryptographically protected with both encryption and integrity protection, you would have two headers on it, the AH and the ESP. But then these two committees sort of didn't really talk to each other. They weren't paying attention to each other. The AH people were really the IPv6 zealots, and the ESP people were security geeks. And so at some point, the ESP people said, it's really dangerous to have encryption without integrity protection. So we'll add optional integrity protection. So the AH people weren't paying attention. So the ESP people added optional integrity protection. And then my favorite RFC ever, the ESP people said, hey, sometimes you might only want integrity protection. So, for performance or something, you don't need encryption. So we should make encryption optional. At that point, the AH people were paying attention and they said, hey, no, you're not allowed to do that. ESP means you must have encryption. If you want integrity only, you have to use AH. So the ESP people said, okay, and we can live with that. Encryption is mandatory, but we can invent any encryption algorithm we want, right? And so the AH people said, why, certainly, you guys are cryptographers. So they came out with my favorite RFC, which I think is 2401 or something, which is null encryption. And it's a fantastically written RFC. It talks about how flexible this algorithm is. It works with any key size. You don't even have to agree on the key. It's very fast, and it even has some test data to test your implementation against. So anyway, what's different about the integrity protection of ESP versus AH is that ESP protects the packet that's inside of the IP header, whereas AH, one of the goals was let's break nets. And so the AH integrity protection also includes the IP header, so that if a NAT were to replace the source and destination address, the destination would receive the packet, but it would reject it because the integrity check wouldn't work. And the vision was that once they deployed this wondrous AH thing, people would say, hey, but it's not working with the nets, let's get rid of nets. But much more likely scenario is that people would say, hey, everything was working, and then you deployed this thing and things are breaking, get rid of that thing. But it doesn't matter anyway, because ESP just works, so you don't need AH. But NATs are actually good. Even if we had infinite addresses, NAT enhances security. It also allows different types of addresses in different portions of the network. So in summary, there were all these arguments about CSMA-CD versus token ring versus token bus, and they're all irrelevant. I mean, even today, I sometimes hang out with old timers that say, oh boy, the industry dodged a bullet with not, had they adopted token ring, boy, it's sort of like civilization could not have worked without English. Right, but especially because we're not using the CSMA-CD thing, that's kind of irrelevant. Both DHCP and NAT, which I've waxed rhapsodic about, they would work just fine with any layer 3 protocol, including CLNP. And the question is, would people have thought of inventing it? And let's see, so closing thoughts, tribalism is bad. I wish we didn't do that. The technology that wins isn't necessarily the best technology. Auto configuration is good, especially I like it because I sort of hate technology. And you should know what problem you're solving. So in my book, I have these little boxes that are real world analogies to the point I'm trying to make. So for instance, for scalability, I talk about the wine glass clicking protocol, which works fine if you have 6 people, but if you have 12 people, everyone has to click, that doesn't make any sense. So the one that's absolutely everybody's favorite, and it's 100% true, is when I was trying to illustrate that you should know what problem you're solving before you try to solve it. This industry, people sort of hear a vague idea, they start writing code and it doesn't work. In all cases, they add more stuff and they wind up with this super complicated thing. So the thing that will forever cement in your mind that you should know what problem you're solving before you try to solve it is that when my son was 3, he ran up to me crying, holding up his hand, saying, my hand. So I took it and I kissed it a few times. What's the matter, honey? Did you hurt it? And he said, no, I got pee on it. So as I said, I have another slide full of things I could rant about, but if we have questions, that's fine too. So Oh, rant? Well, okay. So let's see, what can I, Security is built into IPv6, but it's just an add-on to IPv4. Where did that come from? Well, the IPsec spec says that it's mandatory to implement for IPv6 and optional for IPv4. And it's not like IPsec works better with one than the other. It's just words in the spec. And just because there's words in a spec, it turned out that, at least when people were saying this all the time, there were more implementations of IPv6 without IPsec than with IPsec. There were more implementations of IPsec for IPv4 than for IPv6. And furthermore, IPsec is not equivalent to security. There's, like anything you can do with IPsec, you can do with TLS or SSL. So it's, it's just kind of this nonsense thing. So let's see, what else can I talk about? Quantum and post-quantum. So it's sort of funny, these misconceptions that people have. So they know that quantum is, a quantum computer is like a gazillion times faster than a classical computer. You run the same program on the quantum computer and it'll just be like so much faster. And this is, completely untrue. But at any rate, quantum is like really hard to understand. So, like eventually all our laptops will be too slow, and so we'll all be using quantum laptops. And then, this is all not true, by the way. And then they hear about post-quantum, and my goodness, you have to be like a genius to understand quantum, so you have to be like a super, super genius to understand post-quantum. So post-quantum is a term that I really, I'm annoyed at NIST for calling replacement public key algorithms, calling them post-quantum. So if we had a quantum computer that was sufficiently large, it would make the currently deployed public key algorithms, RSA and elliptic curves, insecure, so we have to replace them with something else. And so they're calling the something else, which are just normal old algorithms running on a normal computer, but just based on different math and factoring, they're calling them post-quantum. So anyway, and internet security. I love this thing. So we know how to do security. The theory is beautiful. So if I want to talk to some website, let's say Bank of America, it gets a DNS name and it gets a certificate. And my laptop, I say, talk to Bank of America, and it sends the certificate and wondrous protocols, wonderful cryptography, and everything just works. Well, that's in theory. In practice, I wanted to renew my Washington State driver's license, and I knew you could do it online. So I Googled renew Washington State driver's license. And the first search thing, which is always the right one, had I bothered to look at this huge URL, it had a perfectly reasonable DNS name in it, which was something like washingtonlicensing.org. So I clicked on it, and it was this wonderful website with like happy pictures of really happy people that you could click on for renew your license, replace a lost license, get a new license, whatever. And so I clicked on renew license. It asked me everything I expected, my address, my license number, and my credit card number. And then a few days later, the fraud department of my bank called me up and said, there's all these charges. Are these legitimate? And I realized what must have happened. And they said, they said, we'll disallow all those charges and give you a new credit card. So what's really amazing is that there's zero security there, because humans don't start out by typing a DNS name. So, the DNS name was, wa.dmv.gov or something. Why was I, as a human, supposed to know that? So at any rate, I should let people ask some questions, and if there's any time, I'll rant about some of these things. So, okay.
Excellent talk. Thank you very much. Alan Hannon, I'm retired. I worked at a network company called UUNet back in '96. And my boss's boss was a gentleman named Heidi Heiden. I think there's a quote that history is written by the winners, but I remember I was told that Heidi Heiden was instrumental in choosing IP over CLNP, or
IPv6?
I'm sorry, TCP over CLNP.
No,
there's any truth to
TCP
that.
would have, for choosing to run TCP over CLNP?
I think I butchered the question entirely, but that's right.
Okay, because TCP is not a replacement for CLNP.
Okay,
It's
I'm trying to make
IPv6 and, yeah.
Okay.
Okay.
But there was a choice to not use CLNP in lieu of something else.
Right. They didn't want to use CLNP. Instead, they wanted to design something new that was going to be wondrously better.
Okay.
Yeah.
So given that I've terribly butchered my question, I'll restate it. I was told that Heidi Heiden was the one that caused the internet to use IP and not to go down that route. Is there any veracity to that?
There were lots of people. There weren't that many, but they were very vocal. So I'm not sure there's any one person that should take the credit for that decision.
Okay. Thanks.
Yeah.
Hi, Lee Howard from IPv4.global by Hilco Stream Bank, which ironically, I'm the author of an internet draft trying to declare IPv4 historic. It seems, so you said NAT is good, it provides security. I've read many times that most implementations of NAT as implemented in the wild open a full cone NAT, meaning once you have a connection to something, anything else can come in. And my observation is that any device that's on has a connection to something. I don't know if that's true, but so I wanted to ask, do you know if that's true? And is that, and then so therefore, would we still argue that NATs provide enhanced security?
Right. So I'm not sure whether it's true. I was actually wondering that myself. You can certainly implement it so that when you have the entry for replacing G's address with it could be a 4-tuple or whatever that also says when this guy is talking to that guy, I'm going to have this entry. In which case it would not be true that once you talk to somebody, anybody can talk to you. So I don't know if the majority of implementations do one thing versus the other, especially because nobody wanted to help NATs by writing down what they do. But it could work either way, and it's certainly preferable. It takes more table space if you give a global address specifically for two communicating pairs.
Thank you, yeah.
I'm going to jump with other virtual questions. So we also have some virtual questions. We're going to try and jump back and forth between you guys and the mic and
Go
the
for it.
virtual ones. James Har wanted to know, what do you make of the networking world's effect to use route Ethernet by tunneling it, EVPN and the like?
Okay. I'm not sure what to say about that. It's sort of very weird, these layering things. So, like run everything over HTTP because it's firewall friendly. What does that mean? It's not like it's easier for a firewall to forward HTTP, but in general, they allow HTTP traffic through. So if you run IP on top of HTTP, so you can do anything, what layer is what. So indeed, you could tunnel Ethernet so that you could have two Ethernets and connect them via an IP tunnel. You can do that. I'm not sure why anyone would do that, but yeah, anyway. So.
Anton Capella, 5 Nines. Thanks for the presentation, Radia. Since I saw your video advertisement on NANOG's website weeks ago for this, I was really happy to see that you're going to be here. So thanks for doing and making the effort for it. Used to be on PC, so taking my PC hat off to you. Question for you. You asked, I think you pointed out on your slide. Can you bring it back up, AV? Is it too late for that? There was one slide. You had a couple principles, things you wanted to wish us to do. Asking questions, I think, about what we're solving was number 1. Is that correct?
I don't quite remember.
Maybe it's too late for that, sorry.
Well, if you could say sort of specifically, you'll remind me what.
Sure. So it seems like there's been a number of interesting junctions, 92, mid-90s, V4, V6 on IP. And we were asking questions like how to run and how to number nodes, essentially, on networks at that time, it seems. Since, say, 2000s, this mobile thing, I have one in my hand here, cell phone and so forth, has been a really, maybe substantially, maybe the only dominant device that we've seen grow and get in the hands of more people in the world than any other type of computer. I would argue that that's the case. Why? To you, Radia, where do we think we haven't asked the right questions about network layers and how to make all this stuff talk? I'm asking this because we had things like mobile IP, RFCs come and go, and no one figured it out, and doing things with DHCP were terrible shims, and it's not good with V6 either. What do you think about that? Are we asking the right questions anymore? I feel like maybe not, but I'd love your perspective on that.
Yeah, well, certainly if we were designing everything from scratch, we'd probably come up with something cleaner. I would hope we would come up with something cleaner. Somebody who actually worked at NASA said once at an IETF meeting after someone was talking about all these shims on top of whatever, he said, well, with enough thrust, anything can fly. So it's sort of like English is a horrible language, but we can kind of make it work. If we need extra words, we'll have extra words and whatever. So I don't think we ever need to totally rip everything apart in order to make the basic infrastructure work. But that example that I gave of how I got taken in by a scam, the fact that there's zero security in practice, how it's the end of truth because you can tune into whatever you want. You have all these bots that decide what they think you're interested in, and they'll give you more and more extreme stuff. It sort of seems like it's the end of civilization. But it's not due to the tiny little tweaks of maybe we should have done this in this layer. So, yeah.
Got it, layer 8 and 9.
Right.
Okay, thank you, Radia.
Thank you.
Our next mobile question we had was from Blake Willis. Thanks for the excellent keynote. We'd love to hear your opinions on the RINA networking model of recursive transport, multiplex, and airflow layers, which is the recursive internet network architecture model, for those of you not familiar with it.
Which includes me.
I didn't know.
So I don't know. It's a good acronym.
He gave us a link, and I'll send it to you later.
Right. Yeah.
Hi, Jeff Osborne, ISC. This was really enjoyable. Thank you so much. I was taking notes and sending links off to people the whole time and saying, you wish you were here. I actually have a 35-year-old question that I realized you probably know the answer to, and I've never gotten one. In 1987, we were putting a T1 link at Tufts University between Medford and the Chinatown Medical School. And T1 was a big deal at the time, and the IP guys were all excited about putting a terminal server down there, as were the DEC guys. And we determined that you couldn't serve terminals on the Ethernet segment running DECnet in Boston without a VAX on it. And I've just wondered ever since then, you didn't need an IP, Unix machine anywhere to serve terminals. Why was that decision made? And does anybody else in the world even remember this?
Yeah, I don't really remember it.
Well,
but let me quickly, let me quickly rant about blockchain. So,
thank you very much.
Given that I have this chance to rant. So everyone knows that blockchain gives you reliability and security somehow. If you take any application and you add blockchain to it, it automatically becomes secure and wonderful. And so I like to tell people, no, don't say, how can I use blockchain? Or what can I do with blockchain? Instead say, what problem am I solving? Look at various types of ways of doing it. And if blockchain, whatever that is the best solution, then by all means use that, though I have yet to see an application that makes sense for. But then I had engineers say to me, oh, I agree with you, but my manager really wants me to use blockchain, so what should I do? I say, well, no, do exactly what I said. Consider the problem, figure out the best technical solution, implement that, and then tell your manager you're using blockchain. They'll never know the difference. So I guess, yeah.
We have one or two more, and I think we have 2 minutes to squeeze it in. John Christoph would like to know if there's any plans for an Interconnections 3rd edition.
Oh, well, for the last unbelievably huge number of years, embarrassingly, I've been working on the 3rd edition of my network security book, which is why I bothered to learn about quantum. And it's pitched at a different layer than anything else leveled than anything else I've seen. Everything on quantum is either breathless hype or it's just throwing a bunch of equations at you and going, ta-da. I like to talk to actual engineers so that, you can actually get an intuition. Now I understand what a program on a quantum computer would look like. And I actually understand Shor's algorithm. Explain how you can factor numbers with it. So yeah, it's been taking a really long time. That should be done pretty soon. But maybe after that, I might do a 3rd edition of Interconnections. If people would like that, it would help if they would send me advice for what kinds of things are out of date. I try not to do things that are like the current RFCs, but instead the basic concepts. So I think the Interconnections holds its own much more than the 2nd edition of the security book did. But yeah, you could probably inspire me to do that if you talked about things that you wish were sort of written about. So, okay, well, thank you so much. I'll be around all week.
Thank you so much, Radia, for your time and your presentation today. It really was wonderful. Let's give her one more round of applause.